Yes, I would like to first thank the organizer for inviting me to give a talk here. My talk is going to be a little bit different from the rest of the talks. It's mostly related to this part of the conference web page, as well as higher order topological phases. So I'm talking about the higher order topological phases. The reference for my work is here, and this is the work that I've done in collaboration with Tian He and Taylor Hughes at University of Illinois. But myself, I'm currently a postdoc at William & Mary. All right, so what is the higher order Weyl semimetal? Before that, let's quickly review what's the Weyl semimetals. I think everybody knows, but just to understand the notations here, in terms of the phase diagram, we call a Weyl node a transition point between a phase which has a zero Chern number and the phase that does not have zero Chern number or non-zero Chern number. So basically, in the region that you have non-zero Chern number, then you have a Fermi arcs that's going to connect between the plus and minus monopole charges of the Weyl nodes. If you have additional symmetries in the system, then you can essentially double down your Weyl nodes and form some Dirac nodes. They are not protected in a conventional way, symmetric way, because if you really go around the low energy point of the Weyl node, you will see it's that there's no term that you can add to gap out these Weyl nodes. The only way that you can gap out the Weyl nodes is that just bring them together and gap them out. So now, this is the conventional Weyl semimetals which been here at least over the last 6-7 years. There's another branch of the topological phases which considered as a new direction. It's a higher order topological phases. Particularly in this talk, I'm focusing on the higher order Dirac semimetals. Then I will start adding perturbation to produce higher order Weyl semimetals. The particular model of the higher order Dirac semimetals that I'm going to start with is this model, which is here. This is the reference, which essentially what they did is that they took the 2D higher order TIs, which is this model. They call it often quadruple insulators, and they stacked them up. So this is the Hamiltonian of the regular 2D higher order TI. Then what you're going to do after the stacking is that essentially you're modifying your hopping term along the KZ direction in this way. So sort of type of symmetries which are really important for us is the C4Z, time resource symmetry, and inversion symmetries. Here, if you the way that we can understand now the phase diagram of this higher order Dirac semimetals is that by tuning this gamma, this hopping, essentially you're going to go from a phase transition from a trivial phase to the phase that has a non-zero quadruple moment. Quadruple moment is a typical invariant, one of the typical invariants that people use for higher order topological phases. The model that we're working on it, starting with it, has 2 Dirac nodes in the bulk. Surfaces are fully gapped, and the hinge states you have connecting a hinge arc. We call it hinge arc, connecting 2 Dirac nodes on the hinges. So this is our starting point. Now we can start to, similar to the case of conventional Weyl semimetals, you can start adding a different type of perturbation to the system to produce split the nodes, Dirac nodes. There are 3 different types here, as you can see. Particularly, I'm going to focus only on these 2, which are C4 symmetric, and the Weyl nodes appear only along the KZ direction. And I will explain how the boundary would look like for each one of them. So let's start from the inversion symmetric higher order Weyl semimetals. For inversion symmetric higher order Weyl semimetals, perturbation that I'm adding is this. And this perturbation is going to break the time reversal symmetry, but it's going to preserve inversion and C4Z. Now let's look at how the phase diagram of the higher order Dirac semimetal changes once you add this perturbation. Once you do that, now the new phase diagram is this, and now I can get 3 different configuration of the nodes. The first configuration is this, which essentially the blue dots are conventional Weyl nodes, the first, what we call it first order Weyl nodes, and the red dots are second order Weyl nodes. As you can see, the blue dots are phase transition point between trivial to the non-zero Chern number. Now, the way that we define a second order Weyl node in this work is that it's a phase transition point between non-zero Chern to the non-zero quadruple. And these three different configurations are like this. So hybrid order, which basically means that you can have a pair of first order while node coexisting with a pair of second order while node. The other one is that you can just simply gap out these two and get the regular first order Weyl semimetal, or you can gap out these two first order nodes and just left off with this only second order Weyl nodes. In terms of the boundary, if you look at the boundary of the regular conventional Weyl points, you will see that on the surface, they are connected with the Fermi arcs, which in one direction is flat, but the other direction is chiral. So that's why you always have to connect a plus to the minus Weyl nodes on the surface. But if you look at the hinge state, which basically means that now I have two open boundary conditions in the system, and I go to the hinge of the system hinge is gap. So there's nothing going on in the hinge. But if I look at the second order Weyl nodes, the situation is like this. Because I starting from a C equal to 1 phase and non-zero Chern phase, essentially on the surface, I'm going to have Fermi arcs on the surface. But in this region, which is gapped in the surface, if you go to the hinge, open up more boundary condition and go to the hinge, you will see that there is hinge states connecting these two nodes on the hinges of the system. In other words, a second order Weyl node is connected by both the surface and hinge Fermi arcs. And the hallmark, the boundary hallmark of the second order Weyl node is that they're going to have a coexisting surface and hinge states. The way that we characterize it, again, it's a through the quadruple moment. This is the way that we calculate the quadruple moment by calculating the polarization of each edge and subtracting from the corner charge. And you can see that in this particular region that you have quadruple half, quadruple is quantized, but the Chern number is 0. In the other parts, the Chern number is non-zero, quadruple is not well-defined with 0. Now, this was the inversion symmetric. How about the time reversal symmetric? I can start to add another k-dependent perturbation here. And instead of breaking time reversal, now I'm breaking inversion symmetry, but I still keep C4 symmetry. So the very first consequence of time reversal symmetry is that the Weyl nodes at opposite k carry same monopole charges. So now the configuration of the charges are different. And another thing is that the minimal number of the charges in the Weyl symmetric phase is always 4, as opposed to inversion symmetric case. So in other words, I cannot gap out each pair of the first order or second order nodes separately in this system. In other words, time reversal symmetry forces the second order Weyl nodes to coexist with the first order Weyl nodes. This is particularly could be very interesting, knob in future experiments to see. Then we can have essentially both of these nodes in same systems. But one thing that I would like to stress here is that if you look at the boundaries of this particular time reversal symmetric case, you will see that the surfaces, they have regular Fermi arcs connecting the minus to the plus or plus to the minus on the surface. But on the hinge, you will see they are connecting 2 minus. The reason is that as opposed to the surface, which is really, these Fermi arcs are 2-dimensional and they have chirality and they carry chirality, these guys on the hinge, they are perfect flat bands and they don't carry any chirality. So they can connect 2 nodes of the same monopole charge without violating these chiral charge. That's also another particularly very different intrinsic property for higher order Weyl semimetals. Now, of course, I can try to add perturbations to tilt this system. So if I add this perturbation like that, the identity perturbation, I can tilt these nodes in my model. If it's pi over 2, I can get type 2 Weyl nodes, higher order Weyl nodes. If I add pi over 5, interestingly, I can get hybrid Weyl nodes, which basically means that each pair of Weyl nodes, one of them is type 1, one of them is type 2. And all of them is just controlled with this theta. There are other models that you can look at my paper if you want for details, but there are other models that you can have a different configuration of monopole charges. So it's not necessarily you have to have nodes along the KZ, but we call them extrinsic higher order Weyl semimetals because there is not good symmetry for quantization of the quadrupole in those systems. Now, okay, so now that we know what's the definition of the second order Weyl nodes and how boundary looks like, let's think of a couple of the physical implication of it. One thing that we can do is that, as I explained, we can try to bring up these two nodes together or put them on top of each other in a plus minus way, the way that is shown here, and gap out this Weyl nodes. And the resulting gapped phase typically has interesting properties. What we're going to do here is that we're going to ask the question that if I have a first order Weyl node and gap it out with a second order Weyl nodes, how are they going to behave? This is the first part. So what we're going to do is that I build this model. I put a regular Weyl semimetal here and a higher order Weyl semimetal here and try to hybridize them. But we have to be careful to tune these gamma zero and hopping terms and these perturbation M in a way that the plus and minus charges are on top of each other. Then this, once you turn on this T, now system is fully gapped in the bulk. So if I do that, the resulting phase is very interesting. On the surface, you will end up with two drag cones, which are helical drag cones on the surface. But in the same time, you're going to get these flat hinge states on the hinge. So there is a coexisting surface drag cones and flat hinge. But the way that they are interesting, and we call them hybrid order topologically insulator, is that these two are completely topologically protected with different symmetries. So they are topologically independent. To see that, let's look at this perturbations. Let's add the perturbation that breaks the C4 symmetry. Breaks the surface symmetries, which turns out to be a combination of time reversal and mirror symmetries on the surface, but preserve the C4. As you can see that in this scenario, surface is gapped out, but the hinges are preserved. I can do vice versa. I can try to add a perturbation that breaks the C4, but preserves this mx times T. And you will see that now I keep the helical cones, but I break, open up this gap on the hinges. There are more physical way to do that instead of just putting them up together the way that I showed. One physical way that experimentally it's possible to do is that introducing charge density waves. If let's say I'm introducing a charge density order here, for the first order Weyl semimetal inversion symmetrics Weyl CW, if I do that, the resulting phase has a bulk gap. Surfaces, I'm going to get surfaces all over the billion zone, flat surface all over the billion zone, but no hinges, which basically means now the resulting phase is a stack of churn insulators. Now, if I do the same thing for the higher order Weyl semimetal, I'm going to end up with the flat arcs all over the surface and hinge arcs all over the surface. In other words, you can call them the stack of 2D hybrid TI, which has both this edge and a corner in the system. But for the time reversal symmetric case, as I explained, I cannot do gap out each pair separately. So I have both in same time, both the type of nodes, first order and second order nodes in the same time. And what's going to happen is that once you introduce the CW order, essentially you're going to gap out the first order Weyl nodes automatically with the second order Weyl nodes in the system, which is a one physical realization for the scenario that explains. So the resulting phase has this helical surface states and hinges states in the same time. And you can see that they are indeed localized at the corners and hinges.
2 more minutes.
Yes, now I'm talking very quickly about the second order Weyl semimetals. When you have the electromagnetic response, I can introduce a flux here in the system. If you do that, you will see that by introducing the flux, you will essentially going to get a competition between the charge on the flux and charge on the hinge in this way. So you're going to get the quantization of the charge on the hinge, overall charge of the system because of the competition of the QF and QH. And you see that by moving the Weyl nodes, the overall charge of the system doesn't change, but since the charge of the hinge is going to increase, it forces to charge on the flux, even though they are especially completely different, to reduce. So you get a competition between the flux charge and the hinge charge, which is, you don't see it in the regular Weyl semimetals. And there are, of course, experimental aspects. One way is through the Flux mechanism. I'm not going to talk about it, but simple Flux mechanism show you that you can get these phases as experimental realization. And I'm going to also talk a little bit about very quickly some of these recent experiments, and you can see that there are done some experiments, at least in the metamaterial system, to try to realize this higher order direct semimetal and Weyl semimetal. Particularly this paper, it's used exactly the same Hamiltonian that I've showed you, and they did and they indeed found this higher order Weyl semimetals experimentally. And this is my conclusion, and thank you for your time.
Thanks for the really nice talk. We'll have questions later.